Okay, so we're looking at page 3 now of the notes for section 3.3. We're still trying to find zeros of polynomial functions. So this example, number 8, they give us a polynomial of degree 4, so we know there's going to be 4 solutions. The solution they give us, though, is a complex solution this time. All right, so the complex conjugate theorem that we just talked about said that if 2 plus I is a solution, then we know 2 minus I must also be a solution. Okay. So what they want us to do is find the other solutions. Now, I mean, we could look at the factors of 50 and do synthetic division. However, with this type of problem, often the solutions are not rational. So maybe the other two are complex. So they might be rational, they might not be. So we don't know. And so if we have 2 solutions and a degree 4, then we have some options. We have 2 different methods that we're going to do. One is using synthetic division, but not trial and error. It's using synthetic division, dividing by the solutions that we have, dividing by the zeros that we know. And so this is a little different. We haven't done synthetic division with complex numbers before. Okay, so that's this method. The other one is we're going to FOIL these, come up with binomials, and we'll FOIL those together. We'll explain it when we get to it. So let's start with the first method. So the first method is going to use synthetic division. All right, so what we do is we put the entire complex number in there. So it's 2 plus I. We put the solution in there, right? So up to this point, it's always been like a 2 or a negative 4, but now we put the whole thing. And then we put the numbers next to it. So that's going to be a 1, negative 1, negative 17, 55, and negative 50. Now we're not using sort of that newer method of synthetic division because we know that this is a root, a solution, a 0. And so when we synthetically divide, we know we ought to get a 0 here, right? Because we know this is a solution. Unlike if we were just trying all the factors of 50, then we would hope to find one that had a 0, and that would say that this is a solution. But we know this is a solution because they gave that to us. Okay, so this part right here can get a little complicated. So we bring down the 1 like we normally would in synthetic division, and then we multiply these 2 together. And that result goes up here. So we have 2 plus I. All right, so that's a purely real plus and a complex. So we add the real parts, and then of course we don't have anything to add to the I for we add the real parts, and then the complex part just follows behind. And so this will be 1 plus I. Okay, now it starts getting complicated. I've got to multiply this by this, so we're foiling it, right? So take a second and do that. I'm going to pause the video, do that, put the result up here. All right, so that ends up being 1 plus 3i. And then I add down, and so that's going to be negative 16 plus 3i. And then pause the video again, multiply these together. That ends up being negative 35 minus 10i. And when we add those up, we get, should have given myself a little more room here, 20 minus that 10i. All right, and then finally multiply these 2 together, FOIL those together, and then end up giving us a 50, which indeed gives us our 0 that we were kind of knew should be coming, all right, because that is a solution. Now notice the depressed polynomial doesn't have integer coefficients. These are complex numbers, but don't worry, just have a little faith. Now we're going to divide that depressed polynomial by the other complex 0. 2 minus I. Now this one's a little bit faster and easier than the first one was. All right. And so again, we bring down the 1, Now you'll find that there are no more complex numbers in our results. When I multiply 1 by 2 minus I get 2 minus I. And when I add, notice the imaginary parts go away. And this just gives me 3. And then when I multiply, that gives me 6 minus 3i. Again, the 3i's are going to cancel. This leaves me with negative 10. When I multiply that, I get negative 20. And I get plus 10i. So indeed, those cancel, leaving me with 0. Okay? So we've taken this polynomial function of degree 4, we've divided it by 2 of the zeros, we have a depressed polynomial of degree 2. So this is going to be x squared plus 3x minus 10 equals 0, and we need to find the 2 solutions. Now we can just use factoring, or if factoring doesn't work, we can use the quadratic formula. But I think this factors. This will be x and what? Plus 5 and minus 2, I think works. And so, we have our 2 solutions up here, and now we have x equals negative 5, and we have x equals 2. And those are the 4 solutions to that. They gave us one, we found another, right? We know this one's true because of the complex conjugate theorem. And then we found the other 2 here. So a total of 4. They gave us 1. We found 3. Okay. So now let's look at the method for not if we don't use synthetic division. So you probably noticed that the foiling process to get these things up here could be a little bit overwhelming, a little challenging. But let's look at another method that you could use. So I have 2 zeros. And what I could do is, if I knew, like, for example, if I knew one of the zeros was, well, like we said, 2, let's say, then I know I could write that as a binomial x minus 2, right? And so if I know the 0 is 2 plus I can write that as a binomial x minus 2 plus I. So that's like a binomial. It looks like a trinomial, but it's x minus the solution, right? If the solution's 2, I said x minus 2. So I'm doing the same thing. We saw this on the last page. And then the other one would be x minus 2 minus I. And so let's distribute those negatives, and we get x minus 2 minus I, and we get x minus 2 plus I. Now, when I multiply these together, remember, like we saw on the last page, we don't, we would get 9 things, but a lot of them are going to cancel because they have i's in them, so those are going to all cancel. So I'm just going to write down what we have left. All right, so what do we have? If I FOIL these together, I know I'm going to have an x squared. I know I'm going to have a negative 2x and a negative 2x. That's going to be a negative 4x. And then the xi's and the 2i's, 2i and the xi, those are all going to cancel. So I'm going to have negative 2 and negative 2, that's 4. And then negative I times I, that's plus 1. So that's a plus 5. Okay? So now, the one mistake that a lot of students make at this point is they take this polynomial expression and they say, oh, let's set it equal to 0 and find the zeros, right? Find the solutions. Well, you're going backwards. That would just give you those, right? We just used these 2 zeros to write binomials that we FOILed out and got this quadratic equation. So we don't want to try to solve this thing. That's going backwards. What we want to do is now take the original function and divide it by this. And we're going to use synthetic division. Now, there's not a whole lot of space here, so I'm going to write it sort of tightly. We have x squared minus 4x plus 5, and that gets divided into the original polynomial. So x to the 4th minus x cubed, x cubed minus 17x squared plus 55x minus 50. Okay, and now we're going to use long division. I'm going to write really small in order to fit everything in here. All right, so we ask ourselves, what times x squared gives us x to the fourth? That's x squared. And now I multiply x squared by these three things and put the results here. Let's start over here. That is going to be x to the fourth. And then we're going to have a minus 4x cubed. And then we'll have a plus 5x squared. Now I subtract, but rather than subtract, I always add the opposites. And so let's change the signs of all those. So that is a negative 5x squared there. All right, and so let's add these up. So this will be negative 22x squared, and this will be 3x cubed. Now I bring down the next term, plus 55. And then I ask myself again, what times x squared gives me 3x cubed? And that is a plus 3x. All right, and then I multiply those together, that together with the three terms out in front. So I get 3x cubed. I get negative 12x squared. I get plus 15. And I subtract, only rather than subtract, I'm going to add the opposites. All right, and so that gives me negative 10x squared, gives me plus 40 x. Did I leave? I lost my x's there. Sorry, those should be x's. And 40x. And then we bring down the next term. All right, what times x gives me negative 10x squared? That's negative 10. So you can see I'm getting that depressed polynomial, right? So here, instead of chipping away at it twice with each one individually, we foil the resulting binomials together to get a quadratic, and we use long division. We divide once. But in each case, we get the solution. Let's just keep going here, then. So we have negative 10, we get negative 50. Plus 50, sorry, plus 50. No, that's negative, should be negative 50, yeah, negative 50. So that's negative 50. That is a positive 40x, and this is negative 10x squared. And then, of course, we subtract them. So instead of subtracting, I'm going to add the opposites. And you can see that we get a remainder of 0, which we should. I mean, we should have known that we were going to get a remainder of 0 because this is definitely a factor of the original degree 4 polynomial, right? This quadratic was made from the foiling of the binomials from the complex numbers. So this is definitely a quadratic factor of the original. So not a surprise that we should get 0. We better get 0 here. And then we would just take this answer and factor it like we did over here. So, you know, x plus 5, x minus 2, and set that equal to 0 to get our last two solutions. So again, we have the one solution from the complex 0 theorem, and then we have our two others, x equals negative 5 and x equals 2. Okay, so you know, either way, we have to divide this original polynomial. We can do it one at a time from each of the zeros using complex, the complex zeros using synthetic division until we get down to a depressed polynomial of degree 2. Or we can use those to create a binomial, two binomials that we foil together, and they give us the quadratic, which we know is a factor of this, and that's why we got a remainder of 0. And then that answer is like our depressed polynomial, and we just factor that. Okay, let's move on to Descartes' rule of signs. So this is a sort of a complex theorem, rule, and the first time we read through it, it's probably not going to make a lot of sense, but it'll make more sense as we do an example. Okay. And so this is just another way. Again, this whole lesson is about figuring out how to find zeros. So this rule sort of helps us decide where we should be looking for zeros, whether the zeros, and this helps us specifically say whether we have positive real zeros or negative real zeros. And so what we mean by that, positive real zeros would be zeros that cross out here in the positive x-axis. Negative real zeros would be our function crosses the x-axis in the negative side of the x-axis. And so it's sometimes helpful, depending on the results of the Descartes rule of signs, sometimes helpful. So if I can use this to determine that there are no negative real zeros, then I shouldn't be, when I do my synthetic division trials, I shouldn't be putting in any negative numbers. So it can sometimes minimize the number of trials that we have to go through in order to find our zeros. All right, so let's read through it. So first of all, we have a polynomial function with real coefficients, and the constant is not zero. So this is not zero. The constant is actually there. All right. If the constant was not there, then it's easy enough. We could simply factor an x out and turn that into turn that 4 into a constant, right? And so we would factor an x out, set that x equal to 0. We would know one of our solutions was 0. So when if it's not a constant's not there, and the last term is the linear term, simply divide out an x, and then you can use this this rule. Okay. So first of all, the number of positive real zeros, that's the number of times our graph is going to cross the x-axis in the positive side of the x-axis. Okay, so the number of positive real zeros of f of x equals the number of sign changes, either equals the number of sign changes as you go through the terms, sign changes from the terms, or is less than that number by an even positive number. Okay, so let's look at this. So I've written it two separate ways. This is the A part of our rule, and this is the B, this will be used for the B part of our rule. All right, so let's count the number of sign changes as we go. So is there a sign change from this term to this term? Yes, there is a sign change. Is there a sign change from this term to this term? Yes. Is there a sign change from this term to this term? Yes. Is there a sign change from this term to this term? Yes. So there were 4 sign changes. So that goes in here, the positive. So we have positive, we have negative, and then we are counting complex. Like how many different types of zeros do we have, right? So we have possibility of 4 positive real zeros, or that number decreased by an even number. We're counting how many times it crosses, so we don't have negative counts here. So it's 4. So in this column, we're going to have a 4. It could be decreased by 2, could be decreased by 2 again. So in this column, we can have 4s, 2s, and 0s. Okay. Now let's think about the part B. Part B says the number of negative real zeros. That's how many times it crosses on the negative side of the x-axis. So the number of negative real zeros of the function either equals the number of sign changes from 0 to negative, negative to 0, positive, negative, and negative to positive in the coefficients of f of negative x, right? Or is less than that by an even positive integer. So if I have my function and I'm putting in a negative x, so I'm putting in a negative x, that negative goes away because it's being raised to the 4th power, so this thing ends up staying negative. The next term, put a negative in. It's being raised to the 3rd power. That negative does not go away, and so it will be negative out in front. So I don't care what else is happening. We're not putting values in. We're just putting a negative x in, seeing what happens to the function when I put in a negative x. All right, so I put a negative x into this, and it's being squared. That negative goes away, and so the negative that was here is staying there. And then the next one, negative, is going to counteract that positive and turn it into a negative. And the last one's constant. So how many sign changes? We don't have any. We don't have one here. We don't have one here. And we don't have one here. So there are no sign changes. So that means there are no negative real zeros. So that means if I was trying to find the zeros of this function, I wouldn't be doing in trial and error. I wouldn't be putting in any negative numbers. Okay. So, and then the number of complex in this case is 0. So if there are 4 positive, there are no negatives, there are also no complex. We know the total sum has got to be 4, so the sum of each row has got to be equal to 4. Okay, and so what would that look like possibly? I mean, we don't know what the graph actually looks like exactly, but you know, it's going to be something like it's going up, it's coming down, it's going up, it's coming down, right? So it crosses the x-axis 4 times. That's what, if this was if this row was what was going on, it would look something like this, crossing the x-axis 4 times. In the positive realm, nothing in the negative realm, and no complex. So it looks, it may be something like that. I mean, I'm not drawing that, I'm just saying that's a possibility, if that row is true. All right, what else is possible? Well, we said it's that number or that number decreased by an even positive integer. So it could be a 2. Now, we can't increase. So once it's 0, you can only go below that number. You can't go up. So you can't increase your negative zeros. That's still 0. Now, if we're decreasing this, the complex, yes, those are going to increase. And it's decreasing by an even because complex numbers have to occur in pairs. So there should never be any odd numbers in this column. All right, so what's happening with this one? Well, if that row 2 is what was really going on here, we would have something like this, and then, you know, like that maybe. It has a little squiggle here. So it only really intersects in 2, if that's what happens. But we don't really know until we, you know, if we were to actually find the zeros. All right, and that's not what this theorem is about. This rule is not about finding the actual zeros, but finding the possible number of positive and negative zeros. So to inform us when we go to do our synthetic division, you know, our trial and error kind of part of synthetic division. Okay, and then what else is possible? Well, we could have 0. Again, negatives, never increasing. The number we get when we count it, it's that number or that number decreased by an even number. So we can't increase this. And then this one is 4. So what's that one look like? So it's like, it doesn't intersect at all. It's all down below, let's say. Okay? All right, so let's try one more example of this. It says, how does this help us result finding zeros? Well, if, for example, this one is pretty powerful because I know there's no way I could ever have a negative 0. So we would not be putting in like check, see if negative, you know, check and see if negative 1 is a solution. Check and see if negative 1/2 is a solution. You wouldn't have to check those. Okay? All right. Now, this is actually no guarantee that there are any. You know, this is if there are rational zeros, but there may not be any rational zeros. So, you know, this is what might actually be going on, right? We might have no real zeros. They might all be complex. Okay. So let's do the same thing for this one. So I'm going to do f of negative x over here, and then we'll do f of x over here. So how many sign changes? Count the sign changes as you go across. So we do a plus, we do a negative, and we do complex, so we'll just denote that as an I. All right, so how many sign changes did you get? We have 1, we have 2, we have 3. We have three sign changes. Okay. And now let's do f of negative 2. So let's check. If I put a negative in, again, I don't really care what the function looks like. All I care about is this first term, when I put a negative x in, is it going to be positive or negative? So that negative is being raised to the 5th power. That will be negative. Then the next one. I'm putting a negative in for the 3, a negative in for the x, and that's being raised to the 3rd power. That negative is not going away, and it's interacting with this negative to make it a positive. So the second term will have a positive coefficient. The next one, the negative in the x, that one is going away in the squaring, so the sign doesn't change here. It's still going to be positive. All right, next one, the negative in for x, that's going to change that and make that term negative. And then the last one is negative. Okay, so how many sign changes did we have? Again, I don't care. You don't have to write the function out. Just have to determine, is it going to be positive or negative? So we have 1 sign change. No, we have 1 sign change, and we have no. So we have 2 sign changes here. And remember that the total has got to be 5 because that's our degree. And so we know that one's has to be 0. Okay, so fill in the rest of this table. And pause the video and fill that in, and let's see what you get. All right, so you know that the 3 is either the correct number or it's decreased by an even number, so it's possible that it's 2. Now, this is possible for decreasing too, but let's do one at a time, right? So we know in this column we can have, decrease by 2. Decrease by 2, that would be a 1. All right, so we know in this column we can have either 3s or 1s, and then in this column we can have 2 or 0. Let me not put that in parentheses. I don't want you to think that's an ordered pair or anything. So the possible numbers in this column are 3s and 1. Possible numbers in this column are 2s and 0s. So you need every combination with each number here with each number there. So we did 3, 2. Let's do 1, 2. All right, then what number would go here? That would have to be a 2. All right, so that's all of the possibilities with a 2 in this column. Now, what about if we went down to a 0? So we could have 3. And again, I'm not going up. I'm just saying that's another possibility. We started with 3. We're staying with 3, but let's, instead of decreasing the positive, let's decrease the negative. So that's a possibility. And finally, we could have 1, 0, and 4. Notice all of these have to be even at all times. Those are complex. The complex conjugate theorem tells us that any 0 that's complex has a pair, has its conjugate also. Okay? So these are all the possibilities, right? So this one maybe is a little less helpful. Using the Descartes rule of signs for this problem is a little less helpful. Up here, for example, we knew there were no negatives at least. Here, there's a lot of combinations. So maybe this, for this particular problem, Descartes rule of signs isn't as helpful. Okay? The homework due next class is listed here. Remember, multiples of 3, multiples of 3, multiples of 4.